Welcome to Lecture 4 of our Probability Theory course. Today we're going to explore one of the most important and widely used concepts in all of probability, independent events. Understanding independence is absolutely crucial because it underlies countless real-world applications, from quality control in manufacturing to risk assessment in finance, from medical testing to weather forecasting, and even to everyday decision-making. When we say that two events are independent, we mean that the occurrence of one event does not affect the probability of the other event occurring. This seemingly simple concept has profound implications and leads to elegant mathematical formulas that make probability calculations much simpler and more intuitive. Throughout this lecture, we'll define independence precisely, explore its key properties, learn how to recognize independent events in practice, and see how the multiplication rule simplifies dramatically when events are independent. We'll also examine the important theorem about the probability of at least one event occurring among a set of independent events. By the end of this session, you'll have a solid understanding of this fundamental concept and be able to apply it confidently to a wide range of problems. So let's begin our exploration of independent events and discover why this concept is so essential in the world of probability and statistics. Let's begin by establishing the formal definition of independent events. An event B is said to be independent from an event A if the appearance of event A does not change the probability of event B. In other words, knowing that event A has occurred gives us no new information about the likelihood of event B. Mathematically, this is expressed as the conditional probability of B given A being equal to the unconditional probability of B. We write this as P subscript A of B equals P of B. This condition means that the probability of B remains exactly the same regardless of whether A has occurred or not. Now, an important question arises. Is independence a symmetric property? The answer is yes, and this is a beautiful result that we can prove using the multiplication theorem. We know that the probability of both events occurring can be expressed in two equivalent ways. If B is independent from A, then the conditional probability of B given A equals the unconditional probability of B. Substituting this into our equation and simplifying, we get that the conditional probability of A given B equals the unconditional probability of A. This means that A is also independent from B. Therefore, the property of independence is mutual. If one event doesn't affect the other, then the reverse is also true. This symmetry is a fundamental characteristic of independent events and makes the concept even more powerful and intuitive. This brings us to one of the most practical and frequently used formulas in probability theory, the multiplication rule for independent events. Recall the general multiplication rule we learned in our previous lecture. The probability of both events A and B occurring together is equal to the probability of A times the conditional probability of B given A. However, when events are independent, the conditional probability of B given A simplifies to just the probability of B because the occurrence of A provides no new information about B. Therefore, for independent events, the multiplication rule takes on this beautifully simple form. The probability of A and B occurring together is simply the product of their individual probabilities. This formula is so important that it is actually used as the definition of independent events. Two events are considered independent if the probability of their joint occurrence equals the product of their individual probabilities. If this equality does not hold, then the events are dependent. This definition provides us with a practical way to test for independence and a powerful tool for calculating joint probabilities when events are known to be independent. The simplicity of this formula is one of the reasons why independence is such a valuable concept in probability theory. Whenever you encounter events that don't influence each other, you can simply multiply their probabilities to find the probability of both occurring. To understand independent events better, let's consider a classic example, flipping a coin multiple times. Each coin flip is an independent event. This means the result of one flip does not affect the result of the next flip. If you flip a coin and get heads on the first flip, that doesn't change the probability of getting heads on the second flip. For a fair coin, the probability of getting heads is always 1/2, and the probability of getting tails is also 1/2, regardless of what happened on previous flips. This is a perfect example of independence because the outcome of each toss is completely unrelated to the outcomes of any other tosses. The coin has no memory, so to speak. It doesn't remember what it landed on before, and it doesn't adjust its behavior based on previous results. This independence property makes coin flips an excellent model for understanding probability concepts. In fact, many random processes in the real world behave like independent coin flips, and understanding this principle allows us to analyze complex situations by breaking them down into simpler independent components. The coin flip example also illustrates why independence is such a powerful concept. It allows us to treat each event separately and then combine the results using simple multiplication. Now let's apply what we've learned to a practical example. Suppose we have two guns firing at a target. The probability that the first gun hits the target is 0.8, and the probability that the second gun hits the target is 0.7. We need to find the probability that both guns hit the target simultaneously, which is a joint hit. The key insight here is that the two guns fire independently of each other. The performance of one gun does not affect the performance of the other gun. Whether the first gun hits or misses has no influence on whether the second gun hits or misses. Therefore, the events are independent, and we can apply the multiplication rule for independent events. We simply multiply the probability of the first gun hitting, which is 0.8, by the probability of the second gun hitting, which is 0.7. Multiplying these together gives us 0.56. This means there is a 56% chance that both guns will hit the target on a given attempt. This example is straightforward but powerful because it shows how independence simplifies probability calculations. Instead of needing to consider complex conditional relationships, we just multiply the individual probabilities together. This is why understanding independence is so valuable in practical applications across many different fields. Now let's explore an important remark about independent events. If events A and B are independent, then several other pairs of events are also independent. Specifically, the events A and the complement of B are independent, the complement of A and B are independent, and the complement of A and the complement of B are also independent. This is a very useful property because it allows us to work with complements of events without losing the independence relationship. Let's look at the proof of this remark for one case. We can express event A as the union of two mutually exclusive events, a complement B complement and AB. This means the probability of A equals the probability of A complement B complement plus the probability of AB. Since A and B are independent, the probability of AB equals the probability of A times the probability of B. Using some algebraic manipulation, we can show that the probability of A complement B complement equals the probability of A times the probability of B complement. This proves that the events A and B complement are independent. A similar argument works for the other cases. This property is extremely useful in practice because it means we can freely switch between events and their complements when working with independent events, knowing that the independence relationship will be preserved. Building on this, we have an important corollary. The probability of the joint appearance of several events that are independent in union is equal to the product of the probabilities of these events individually. This extends the multiplication rule from two events to any number of independent events. For example, if we have three independent events A1, A2, and A3, the probability that all three occur is the product of their individual probabilities. Additionally, if events A1, A2 through A subscript n are independent in union, then the opposite events, the complements of A1, A2 through A subscript n, are also independent in union. This is a powerful result because it means we can work with either the original events or their complements and maintain the independence relationship. This property is particularly useful when calculating probabilities involving at least one type problems, which we'll explore later in this lecture. The independence of complements allows us to transform complex probability questions into simpler ones by focusing on the events not occurring instead of the events occurring. This flexibility is one of the reasons why the concept of independence is so fundamental in probability theory and its applications. Let's work through a complete example to see these concepts in action. Suppose we have three boxes, each containing 10 details. The first box contains 8 standard details, the second box contains 7 standard details, and the third box contains 9 standard details. We randomly take one detail from each box, and we want to find the probability that all 3 taken details are standard. First, the probability that a standard detail is taken from the first box is 8 out of 10, which is 0.8. The probability that a standard detail is taken from the second box is 7 out of 10, which is 0.7. And the probability that a standard detail is taken from the third box is 9 out of 10, which is 0.9. Now, since the boxes are independent of each other, the events are independent in union. What happens in one box does not affect what happens in another box. Therefore, we can apply the multiplication rule for independent events. We simply multiply the 3 probabilities together, 0.8 times 0.7 times 0.9. Calculating this gives us 0.504, which means there is a 50.4% chance that all 3 randomly selected details will be standard. This example demonstrates how the multiplication rule extends naturally to any number of independent events and shows how we can solve complex multi-stage problems by simply multiplying individual probabilities. Now we come to one of the most important and practical applications of independent events, finding the probability that at least one event occurs among a set of independent events. There is a theorem that states that the probability of the appearance of at least one of the events A1, A2 through A subscript n, which are independent in union, is equal to 1 minus the product of the probabilities of the opposite events. This is a very clever approach because instead of trying to calculate the probability of at least one event occurring directly, which can be complicated, we calculate the probability that none of the events occur and subtract that from 1. Since the events are independent, the probability that none occur is simply the product of the probabilities of each event not occurring. If each event A subscript I has probability P subscript I of occurring, then the probability of it not occurring is Q subscript I, which equals 1 minus P at subscript I. The probability that at least one event occurs is therefore 1 minus the product of all the Q subscript I values. In the special case where all events have the same probability P, the formula simplifies to 1 minus Q to the power of n, where Q equals 1 minus P. This simplified formula is particularly useful when dealing with multiple identical independent events, such as flipping multiple coins or testing multiple identical components. Let's apply this theorem to a practical example. Suppose we have 3 guns firing at a target, and the probabilities of hitting the target are 0.8 for the first gun, 0.7 for the second gun, and 0.9 for the third gun. We want to find the probability of at least one hit when all 3 guns fire once. The key insight is that each gun's performance is independent of the others. So we first calculate the probabilities of each gun missing. The probability that the first gun misses is 1 minus 0.8, which equals 0.2. The probability that the second gun misses is 1 minus 0.7, which equals 0.3. And the probability that the third gun misses is 1 minus 0.9, which equals 0.1. Now the probability that all 3 guns miss is the product of these individual miss probabilities, 0.2 times 0.3 times 0.1, which equals 0.006. Therefore, the probability of at least one hit is 1 minus 0.006, which equals 0.994. This means there is a 99.4% chance that at least one of the 3 guns will hit the target. This is a remarkably high probability, which makes intuitive sense because even though each individual gun has a chance of missing, the chance that all 3 miss simultaneously is very small. This example beautifully demonstrates the power of the at least one theorem and why it's so useful in practical applications. Let's work through one more example to solidify our understanding. Imagine a typography with 4 flat printing machines. For each machine, the probability that it is working at the present time is 0.9. We need to find the probability that at least one machine is working at the present time. This is a perfect application of our at least one theorem with identical probabilities. First, we identify the events and their complements. The events are that each machine works, and the opposite events are that each machine doesn't work. Since the probability that a machine works is 0.9, the probability that it doesn't work is 1 minus 0.9, which equals 0.1. The events are independent because each machine operates independently of the others. Therefore, the probability that all 4 machines are not working is 0.1 to the power of 4, which is 0.1 times 0.1 times 0.1 times 0.1, equaling 0.0001. Consequently, the probability that at least one machine is working is 1 minus 0.0001, which equals 0.9999. This means there is a 99.99% chance that at least one of the 4 machines is working at any given time. This extremely high probability reflects the redundancy built into the system. With 4 machines, it's very unlikely that all of them would be non-functional simultaneously. This example illustrates why the at least one theorem is so important in reliability engineering and quality control, where we often need to ensure that at least one component of a system is functioning properly.